Andrew Zhang is a current junior and lifer at Harker. Beyond challenging himself through math and science-related activities, he also loves performing arts, such as dance, a cappella, and piano. After his first year in astronomy at the Science Internship Program at UCSC, he became intrigued with a combination of astrophysics and programming. Though research challenges included a lack of background knowledge and unfamiliarity with the language, these were all remedied by close guidance under his mentor. After his freshman year, he got deeply involved in the program and returned again as a sophomore. Michelle Guo is a senior at Irvington High School. Her hobbies include piano, cello, and composing. So now I'm going to turn the stage over to them. Please enjoy.
Hi, my name is Michelle Guo. This is Andrew Zhang. And this is our project on isotopic abundances in the Milky Way, insights into the origin of carbon and neutron-capture elements. 13.7 billion years ago, the Big Bang created only hydrogen, helium, and small amounts of lithium. All other elements heavier than lithium were created inside stars. As stars died, they released their newly synthesized materials into the surrounding interstellar medium, where the newly synthesized elements were incorporated to new stars and new planets. Although lighter elements are created from the simple fusion of nuclei, elements heavier than iron are created through a more complex process called the neutron-capture process. There are two types of neutron-capture processes: the slow S process, which occurs in asymptotic giant branch stars, or the rapid R process that occurs in supernovae. Each of these processes are mutually exclusive, and they produce elements at unique isotopic ratios. So by measuring the isotopic ratios of elements inside stars, we can determine how much of a star's elements came from supernovae and how much came from AGB stars. Currently, there are two competing models called the stellar and classical models that predict these unique isotopic ratios. So in this work, we're trying to evaluate the validity of these models by measuring the isotopic ratios for elements inside stars. We analyze high-resolution spectra for Milky Way halo stars, and the Milky Way halo is the region surrounding the Milky Way that contains a lot of old stars. Our spectra were collected using the 3-meter Shane telescope from the Lick Observatory. So in this project, we calculated the carbon and europium isotopic and elemental abundances. The reason we picked europium to measure in particular is because europium hasn't been very heavily studied, and the europium isotopic ratio doesn't vary much from star to star, so we can use the europium isotope ratio to validate our measurements and to identify any stars with unusual nucleosynthesis. By measuring these isotopic ratios, we can trace the origins of heavier elements from R and S processes of ancestor stars. And we also wanted to evaluate the validity of the stellar and classical models of heavy element nucleosynthesis. So shown here is an overview of our procedures. In order to measure the carbon and europium isotopic and elemental abundances, we had to fit model spectra with observed spectra. Europium and carbon isotopic and elemental abundances affect the overall shape of the spectrum, so we were able to vary the isotopic and elemental abundances until we found the shape that caused the model spectra to best fit the observed spectrum. But before we began to prepare the observed spectra and synthetic spectra, we first had to determine the carbon wavelength suitable for measurement. Shown here is the G-band of the spectrum, which is the region from 4273 angstroms to 4333 angstroms. And this is the region typically used by astronomers to measure carbon because of its high saturation in carbon-hydrogen molecules. There are three components to the G-band, the R, Q, and B band. However, we found that the Q band was too heavily saturated in carbon-hydrogen molecules, making it less sensitive to carbon abundance changes. We also found that the Q band had very little isotopic splitting, causing it to be less sensitive to isotopic changes as well. So instead, we went ahead and used the R and P band for spectral comparison and generation.
To compare our synthetic spectra and the observed spectra, we had to do some preparation. And two of the things we had to do first were continuum division and Doppler shifting. So Doppler shifting, it takes into account the fact that the wavelengths of a spectra are shifted depending on how fast a galaxy or a specific star is moving relative to the Earth in the radial direction. And so by dividing out a factor that changes by the velocity of the star, we can shift the wavelength array so that it matches the synthetic spectra, which is without any Doppler shift. And continuum division is necessary because the shape of an observed spectrum is not normalized to 1. That is to say, it can go above and below 1 in special cases. And so one thing we had to do was we had to make sure that the perfectly normalized synthetic spectra had the same shape as the observed spectrum. And we do this by finding the continuum of the observed spectrum and multiplying it into the synthetic spectrum. So here we have MOOG. MOOG is the program we use to generate our synthetic spectra. It takes in a few parameters, including a line list, which is essentially a list of the interactions between electrons, their energy levels, and the light that they absorb. And it gives us information about how these atoms and their electrons absorb wavelengths of light and create these absorption lines in the spectrum of the star. The model atmosphere takes in parameters of the star that we're looking at. We have information about the effective temperature, the surface gravity, turbulence, and we can vary any information about the elemental abundance and isotopic ratio. And by varying these, we can determine the best fit. Another thing we had to overcome was the fact that the wavelengths array are not the same, and so it's not possible to compare two arrays that have different dimensions. So this is what rebinning does. It essentially takes the observed spectrum's wavelength array and the synthetic spectrum's wavelength array and matches them so that we can computationally compare them. Imagine that the stars let out light, and this light is like water. And we're catching this water in buckets, which are essentially flattened out because of how much we capture. And so each of these points represents a point on the curve, which represents, in turn, our spectrum. But we don't want these buckets. Say we want two sets of buckets that are exactly the same. And what we can do is we can distribute the values in our flux so that it shares the same function as our spectrum, but doesn't have to have the limitations of two different wavelength arrays. Finally, we had to have resolution determination and smoothing to account for our final changes. And the way we determine resolution of a spectrum is by taking the wavelength of a line and dividing it by the full width at half maximum absorption. And this is okay because in a shell spectrograph, such as the 3-meter Shane telescope, it conserves the spectrum's resolution across the entire star. And so what we can do is by finding the iron lines and finding their resolutions and averaging them across one spectrum, we can find a working resolution for that star. And we can convolve it with a Gaussian kernel with a specific resolution to match the synthetic spectra, which is initially noiseless, to the to the observed spectra, which will inherently have some noise.
So one thing that makes our Europium measurements different from previous works calculating Europium measurements is that we use something called hyperfine line modeling, and it accounts for the interactions between the electrons and the protons in the nucleus. And this is very important when we're dealing with different isotopes, because the different number of neutrons in the nucleus causes slight changes in the structure of the nucleus, and therefore our Europium absorption lines are slightly off-centered. So we use hyperfine line modeling, and we modified the line lists that were used to generate synthetic spectra in order to model the absorption lines of Europium more closely. The final step of our calculations involved fitting the model spectra with the observed spectra in a chi-square minimization routine, and this was calculated using a program called MPFIT. And as mentioned before, there were a few fixed parameters of the synthetic spectra that we held fixed, and those included surface gravity, effective temperature, and the turbulence of the star. But what we didn't know were the elemental and isotopic abundances of the star. And so we varied those accordingly until we found the best fit between the model and observed spectrum. And that corresponded to the least chi-square value that MPFIT returned. We also determined the errors on our spectra, and this was determined through MPFIT as well. And even though the signal-to-noise ratio on our spectra were pretty high, we still went ahead to determine the errors because Europium has a lot of room for error since its lines are extremely weak, and typically in a spectrum, there's only one Europium line available for measurement.
So here we start looking at the RNS process and how they contribute in respect to the classical and stellar model. So Europium has two stable isotopes, Europium 151 and Europium 153. And F151 denotes the fraction of Europium 151 out of all the Europium in a star. So as you can see here, the classical and stellar model seem to contradict in what is the R and S process contradictions. The R process is the same. However, the S process takes a different direction for each of the two processes. And what these R and S process lines mean is what is the predicted isotopic ratio for a star that has only had entirely R or entirely S contribution in the past. And so logically, a star's isotopic ratio should be somewhere in between those two lines. Furthermore, as we stated before, over time, the R process should tend towards the S process because the S process stars, such as the AGB stars, produce their elements much later and therefore have a later point of activation before overwhelming the R process contribution. So in context of our model and all these information, we can disprove the stellar S process because our data depicts that there's a downward trend. And in order for the stellar model to be corroborated, it requires an upward trend. Otherwise, it would not go from R to S process. However, one problem that we see is that the classical S process is not actually reached. On the left, we have the same graph as before. On the right, we have a study from literature from Mashinkima et al. They're looking at barium isotopes, which have been previously used to great extent to study RNS process because their lines are much more prevalent and their lines are actually much stronger than those of Europium, so they have less room for error. However, as you can see, their stars actually reach the lower limit of the S process, whereas ours only reach about halfway. And we think this is because since Europium has been so rarely studied before, that all these models, and especially because of the difficulty in measuring Europium, that the stellar and classical model are to an extent inaccurate for Europium because of all of these difficulties. And we think that the classical S process has a correct directionality in that it goes down with respect to the R process. However, we believe that it should be a little higher to somewhere around the values of 0.2 or 0.3.
So shown here are our carbon isotope ratios. And carbon has two stable isotopes, carbon-12 and carbon-13. So we measured the ratio of carbon-12 to carbon-13. And as you can see in this graph, a lot of our stars hit the upper limit of 50. And the reason we have upper limits for 50 is because above 50, it's really difficult to differentiate between different isotope values. And what you can see is that most of the stars in our sample have that upper limit of 50. And since AGB stars create both carbon-12 and carbon-13, but supernovae create only carbon-12, we conclude that these high carbon isotope ratios correspond to most of our stars coming from supernovae explosions. We also compared our carbon abundances to two previous works of literature. On the left, you see Lucatello et al. 2006, and on the top right, you see Frebel 2010. And they also studied carbon abundances for Milky Way halo stars. But the reason why their measurements are so far to the left is because they were studying specifically what is called carbon-enhanced metal poor stars. From our comparisons, we concluded that our measurements are more precise than those previously measured. And we also measured the slope of our carbon abundance measurements, and we found a slope of negative 0.123, which is very close to 0, which demonstrates that carbon tracks iron very closely and that most of the carbon in our stars originated from supernovae. Shown here are the Europium abundances that we calculated, and we compared them to previous measurements made by Fulbright 2000. And as you can see, there's quite a huge discrepancy between our data and Fulbright's data, and we think that this may be due to the fact that we were using updated line lists in this project, and that Europium in general is pretty difficult to measure.
So in conclusion, most of our carbon in Europium shows that All of these elements were primarily created in our process stars, which happened during a supernova. And we also found that the classical model, although it's better at predicting it's better than the stellar model for predicting Europium isotopic ratios, that it's still inaccurate because of the lack of research. And we also found that our carbon abundances validate our measurements and support prior measurements in literature. Thank you. And we'd like to thank our mentors, Dr. Evan Kirby, who's working at UC Irvine, Dr. Rajaguhata Kurta at UCSC, and we'd also like to thank the UCSC Science Internship Program, the Harker School, and Chris Spenner, who helped us review.